All right, let's talk about angle bisectors. All right, so we're going to bisect an angle, meaning we're going to take an angle and we're going to split it into two equal parts. So I'm just going to kind of draw a random angle formed by these two rays. Okay, and then in red, I'm just going to do my best here. Let's say that is the angle bisector. Okay, and what that means is that that angle is congruent to that angle. I've split it into two. Okay, so what do we know? Well, actually, we first have to establish this. So if I draw any line, so tangent here, draw a line, and then pick any point you want. I don't care. Point here, point here, point here, point here, dot. There's the point. Find me the shortest distance from the point to the line. So like you're lost and there's a road here. You're like, oh, there's a road that way. What direction do you walk to make your walk the shortest? Well, it turns out that you want to walk such that you're perpendicular, meaning with the opposite reciprocal slope of that. The shortest distance, shortest, not the only distance, obviously you could walk any distance you want, but the shortest distance is the distance such that you form a perpendicular line, right? If you walked that red versus that guy, versus that guy, longer, shorter, best, right? It's the shortest distance. So come back over here. As long as we understand that the shortest distance from a point to a side is perpendicular, then we can do this. Check this out. I'm going to pick any point I want on the angle bisector. And I want to go to the side. If I take the shortest distance from this point to this side, what angle am I going to form? 90 degrees to the conversation we just had over here. And I'm going to go to this side. Shortest angle, 90 degrees. All right, take a look at this triangle. This triangle is 90 degrees and an angle, and then it's got this side length. And the other triangle is the exact same. 90, single, single side. 90, single, single side. So what do we know about those two triangles for sure? And how? We know them, they're congruent. Check it out. Angle, angle, side. Angle, angle, side proves that the triangles are congruent. If the triangles are congruent, we also then know that corresponding parts of congruent triangles are congruent, which tells us what? It tells us that these distances are the same because the triangles are congruent, meaning every single part of the triangle is congruent to its corresponding part in the other triangle, right? These two. So what can we say? Any point on the angle bisector is equidistant from the sides. Any random point, pick any point you want, is equidistant from each side. Right? I can pick down here. I can pick right there. Anywhere you pick that point. That distance has to be the same. And that's the angle bisector theorem. And check this out. We're going to use it to do something else with triangles and circles. Okay? So I'm going to draw another sweet triangle. Okay? I'm going to draw the three angle bisectors. As a reminder, the circumcenter one, you're going to draw three perpendicular bisectors. Here I'm going to draw three angle bisectors. Okay, so take this angle, bisect it, something like that. Take this angle, bisect it. Again, I'm doing my best here. Take this angle and bisect it. Somewhere in there, let's pretend all those hit. They're really close to hitting, and boom. Okay. We okay that that red point is actually located on all three angle bisectors. Okay. So the three reds are angle bisectors of the triangle with vertices, A, B, C, or whatever. All right, think it through. What did we say up here? Any point on the angle bisector is equidistant from each side. So this point, let's focus on this. This red bisects this angle. Okay, That means this point is equidistant from those two sides. So let's go over to that side. Shortest distance is perpendicular, and shortest distance is perpendicular. And then what do we know about those two things? Those two things have to be congruent. Okay, now let's look at this guy, this angle bisector. This point also lies on that angle bisector, which means it's equidistant from those two sides, right? This angle, this is the angle bisector. Boom. We could do the same thing over here. This is on this angle bisector, so that distance have to be the same. Now, do these things hit in the midpoint? No. But they are perpendicular to the side, because that is how you get to the side the fastest. And these three distances are the same, meaning the InCenter, I know, creative name, right? The InCenter is of another version of the center of a circle. It's equidistant to each side of the triangle. Okay, which is also another cool property. And then if you think about it, it actually makes a circle inside, inscribed. Ooh, that was a pretty good circle for me. Inside the triangle, right? That distance is the radius of that circle. The triangle inscribes the circle. Where if you looked at the circumcenter, flash that back at you. In this one, right, we did perpendicular bisectors, and we actually got a circle to inscribe the triangle. This guy is the triangle inscribes the circle, meaning the circle is inside. This is the InCenter. The InCenter is the intersection of the three angle bisectors. Because they're angle bisectors, they're equidistant from the side. So, like, if you had three roads and you were there, it actually wouldn't matter what road you wanted to go to. You're the closest to all three of those roads at that location. Again, the InCenter is another version of the center of a circle. The InCenter happens to be the intersection of the angle bisectors. And then again, we already talked through why that is true. Okay, so that's InCenter.